Welcome everyone to our session about reliable Kubernetes resource submission and bookkeeping. So let's introduce ourselves first. I'm Yao Lin.
I'm Tiancheng Yin.
So we work in the workflow orchestration team in cloud native compute services, along with other similar Kubernetes-based platforms inside Bloomberg. Yeah, we have a few dedicated team, Kubernetes-based, and we're interested in this whole ecosystem. We maintain a highly available container orchestration that platform for our internal engineers in Bloomberg. The platform itself executes users run to completion workload for general use cases. So typical use case includes like machine learning pipelines, CI/CD pipelines, machine maintenance routines, and financial analysis or any general data processing. So for these use cases, we have both some functional and non-functional requirements. The functional part may be easier. There's observability, scheduling, or eventing. Approval process needs to be integrated into the whole platform to make sure things are properly reviewed before taking effect. But the non-functional can be less obvious, but that is probably the most difficult part in the whole system. Yeah, so in Bloomberg, we value the data center resiliency seriously. So what does that mean? That means if one data center goes down, our platform should be seemingly still working to our users because everything should be highly available by what's available on the other side of the system, another healthy data center. So before diving into technical diagrams, we can first understand what our user is doing with our platform. To the basic, they need to run their workflows. If you are not familiar with Argo workflows, Argo workflow is something you can define your steps, like in DAG. They can be depends on each other or span from each other. Execute containers in particular sequence. For example, I can generate a report first and then persist somewhere, and then finally it notifies me when everything is finished. For that to happen, we need a few other resources available on the cluster it's executed on, such as config map and secrets. And for workflow specifically, there's Argo workflow template and cluster workflow template for the workflow itself to refer to. So let me put an abstraction layer on these things. So for workflow, we just put it as runnables. So it's of a similar concept of other things like Kubernetes native jobs or any other customized jobs. And the other things, because they are expected to be available on the applicable clusters. So we call them deployables. They should be consistent. They should be there whenever needed. Okay. So that's the assets we help manage, but how do we manage that? From a very high level, this is the diagram of a very simplified form. First, we offer a workflow API. In other slides, we may refer it to as user API. This API first handles the mutation request from our users to change things on the cluster. And then the API also exposes the reads endpoint to allow users to retrieve their assets. But things can be a lot more complicated than the single diagram because we have a farm of clusters to manage. Also, diving into those clusters, there are at least 2 data centers for each of the sets that we provide for our users. So if one data center goes down, say the Oscar side, maybe caught on fire, like the airport, or we put one side down for maintenance, then the other side should be able to function as usual. So, and then we can look at what can exactly goes wrong for each of the resource types. For runnables, when our API submits to a cluster, it needs to consider which cluster is more available for more suitable for this workload. Also, it may need to handle slightly more complicated logic like retries if the error seems transient. There can be more feature requests that requires more sophisticated logic. For deployables, well, the consistency is the top concern. How can we guarantee the consistency at the change time and going forward? For example, if the cluster was put down or gets rebuilt, something like that, how can we grab the original expected resource from somewhere else? And then on the other side of this loop, the read request, the difficulty seems similar for runnables and deployables. First of all, if all the read, say the list, it consumes so much CPU resources, if all those requests actually land on the Kubernetes API server itself, then that's too much load. It may even downgrade the performance of the cluster in terms of orchestrating the workflow itself. Also, we need extra layer for approval or auditing purposes, for auditing user actions and the job execution within this cluster. So generally, we need system resiliency on top of these individual clusters. There may be some regulatory requirements in your mind that's related to this setup. There's something existing and something coming up. We won't list all of them right here. So now it's time to get into the solution space. So in order to execute those sophisticated logics, we need to separate the API and the submitter that actually submits things. So first, the API needs to store things in the audit database as user actions. So it serves audit and approval handling purpose. And also, these runnables are actually sent to a message stream for actual processing. The submitter, which is hidden away from our users, will handle those complicated logic like retry, by determining if the error is transient or not. Also, like feature support, say verify if the workflow is still valid for submit after some time. For deployables, things can be similar or slightly different. This shows a slightly different view. The API will only need to put the deployable objects into the audit and the source of truth based on the form they suited. And then there's a syncer service, reads from the source of truth database and actually lands things on the cluster. This setup may seem like a pull model, but that's pure logical. So in practice, you can actually implement a push mode just like what we demonstrated in the last slides. So put them together. These two kinds of resources can be handled differently, but they are hidden away from users. So that's the submitting part. I'll now hand over to my co-speaker for the other half of the loop.
Thanks, Yao. So after the resources land on the cluster, there are multiple post-deployment status tracking use cases that we would like to support. So let's first imagine that we want to build a user interface that displays the execution results as well as the user-defined object of all the in-cluster resources. As we mentioned before, data resiliency is our top priority concern. Therefore, we expect the UI to behave and return the accurate results even though the cluster is down. Moreover, same as all other user-facing interfaces, we want our UI to have low latency and high performance. So, as you could imagine, getting the object and execution results of in-cluster resources requires a lot of interactions with the Kubernetes API server. And then that will increase the latency, and our UI performance could be drastically impacted if our design relies purely on the interactions with the in-cluster Kubernetes API. So another key use cases that we want to support is to preserving the historical transactions of in-cluster Kubernetes resources. Imagine that a user wants to see all the historical updates and versions of a config map in order to better understand what's get changed at what time in order to debug a deployment. Moreover, preserving the historical transactions for resources could help us with auditing purposes by answer the key questions like who made what changes to what resources at what time. So let's first talk about persisting historical transactions. As Yao already mentioned in a couple of slides before, we already persist and preserve the transactions into a highly available database. So for example, if a user wants to make updates into config map, then all the updates attempt will be stored in that database. And now all we need to do is just to expose a user-facing API for the user to retrieve the historical transactions with those given resources. So in order to support the user-facing interface use case, we want our design to be resilient against data center failures. So therefore, we introduced a solution that uses highly available data storage to persist the latest object and execution results in the highly available data storage. So to achieve that, in our workload clusters, we build and deploy a message producer that watches the update, create, and deletes events for certain types of Kubernetes resources and publish those resource information into a message stream. And on the other hand, we have a consumer service that updates the data storage, what we call inventory in this case, based on those type of events. So to give you an example, let's say a user creates a config map in a cluster, and then the resource status watcher will publish an event with type create, as well as the config map spec into the message stream. And then the consumer will receive this message and create a new record in the inventory database. And similarly, if a user deletes a config map, the event of type delete will be published into the message queue, and then the consumer will delete the record from the database. On the other hand, in case of cluster downtime, user can still using this interface, the user-facing API, to interact with the database to retrieve the resource status without any direct interactions with Kubernetes API server in cluster. So this ensures the data resiliency of our design. So, well, this design sounds pretty straightforward. However, we could easily encounter some concurrency issue. So in the next slide, we will go over one of the corner cases scenarios when things could potentially go wrong. So now imagine a situation where a user tries to delete a config map by calling the user API. So the API then interacts with the source of truth database and deletes the resource from the database. Our syncer will then detect such change and delete the resource from the cluster. So in any sunny day cases, when things work as expected, producer will capture the deletion event and consumer will delete the resources from the inventory table. However, imagine what if producer somehow gets out of memory at that time or is being rebooted by someone. So in that case, producer fails to capture the deletion event, and the event won't be published into the message stream. Because the deletion event is actually missing, the consumer, on the other hand, will not be able to delete the record from the inventory table. So this leads to what we call zombie record in the inventory table. And it could cause problem when users try to ask about the resources. For instance, if a user asks about, hey, if my config map still exists in the cluster, the user API will try to get the answer by interacting with the inventory table. Since there's a zombie record, the user will get an answer saying the config map still exists. However, the actual resources was already deleted from the cluster. So to solve this problem, besides the create, update, and delete events, the producer also published hourly snapshot of all the in-cluster resources. You could imagine the snapshot contains a list of Kubernetes object UID as well as the cluster information. The consumer, on the other hand, will take this information and compare with what exists in the inventory table. So if a record exists in the inventory table but not in the hourly snapshot, then we have identified the zombie record. The consumer will delete the record from the inventory table. Now, if a user tries to use the API to ask about the resource again, he will get the correct answer this time. So this method ensures the inventory table is consistent with what actually happened in our Kubernetes cluster. So to summarize, at submission time, we face different challenges for deployables and runnables. We have consistency and disaster recovery challenges for deployables. In order to mitigate those challenges, we built a syncing service to sync deployables from source of truth across all the clusters. To ensure the reliabilities of runnable submission, we built a submitter service that submits runnables to destination cluster from message stream. And then such submitter would retry on transient errors, and it will have additional features like deadline verification. And once the resource lands on the cluster for post-deployment status tracking, we want to build user interface and API with low latency and high resiliency. We also want to preserve historical transactions for auditing purposes and traceability. So to accommodate the design goals and our use case, we implemented in-cluster producer to produce the historical transactions and resources status into a message message stream, and have consumer service that preserve those information in a highly available data storage. And then on the other hand, we have user-facing API and the UI to help the user retrieve those information. So that brings us to the end of our presentation today. Thank you all for joining, and we are now open to questions.